All right, 9.2, we are going to be looking at multi-stage experiments. So in 9.1, every experiment that you looked at, you did the experiment one time, right? You took like one number or one ball out of the hat or something like that. It was always just experimenting and doing something once. So what we're going to do in this section is we're going to do the experiment multiple times. So maybe you draw 2 balls out of the hat. Maybe you select 2 people to go onto that committee. Maybe we're going to do an example. We're going to send people to Hawaii. So yeah, so we're doing multiple people or multiple multiple trials of a single experiment. In order to keep all of that straight, what we're going to be working with are called tree diagrams. So tree diagrams are a sample space model where each outcome is designated by a separate branch. One-stage experiments, like we were doing in 9.1, have an experiment that is over after one step. Two-stage experiments, or you could even say multi-stage experiments, are over after 2 steps, or it could be 3 steps or 4 steps, but you have multiple steps involved. So based on one of the questions you guys asked, remember the question where it had the red, white, and black balls in the basket? So if we were to draw a tree diagram based on that one, let's see if I can remember it right. We had 5 white, we had 2 black, nope, it was 3, wasn't it? 3 black and 2 red. So a tree diagram, depending on the questions that are asked, could be set up in one of 2 ways. We could set up a tree diagram if we're just drawing one thing, where it lists all 3 options out here. Red, black, white. Okay? So you would say, here's my red, here's my black, here's my white, in whichever order you wish, it doesn't really matter. This would be a single stage experiment. What's the probability I draw red? What's the probability I draw black? What's the probability I draw white? And along each branch, because this is what 9.6 is about to tell us, we write the probability. So the red is a 2 out of 10. You can do it reduced or you could do it like this. You could do it in decimal form as well. You could do it as a 0.2 probability instead of a 2/10. The black was 3/10. And then the white is 5/10. Okay, so you're writing the probabilities along the branches. This is what a one-stage experiment looks like. I usually do my diagrams from left to right this way. You can do them top to bottom. So instead of drawing it like this, I could have just as easily drawn it like this. It doesn't matter if it's going vertically or horizontal. It doesn't make any difference. This is one stage. But let's say after you draw that ball, you keep it and you draw a second time. Well, that's what's called a 2-stage experiment. And what it ends up looking like is it ends up looking like 3 more branches off of each branch because there's 3 more possibilities. Now, I'm not going to finish doing out the problem, but you can imagine what this would look like, right? Each one of these would say the same, and we would usually stick with the same order. Red, black, and white, and red, black, and white, red, black, and white. If we've kept the ball, it changes the probabilities. Right? So if I drew a red ball, there's only 1 red ball left. There's also only 9 balls left in the basket. But sometimes we do replacement, which means I draw the ball out and then I put it back and we do it again. And when that happens, then all the probabilities stay the same. It would still be 2 out of 10 and 3 out of 10 and 5 out of 10. So this is basically what a tree diagram looks like. There are some cases as well where you don't necessarily, like let's say we still had the same setup. I'm going to erase it and do an alternate version of it. But every question only asked about red balls. It doesn't ask about the probabilities of white, probabilities of black, nothing like that. It just cares about what happens in terms of the red balls. So if that's the kind of questioning that's happening, another way of drawing your tree diagram is to draw it as red and not red. Why? This is an easier tree diagram to draw. It only has 2 branches. And if I did it a second time, I'd only have 2 branches off of each of the 2 branches instead of 3 off of each of the 3, leaving me with 9. And this only ends up with 4 at the end, right? So it's a good idea to look at the questions that are being asked to decide, do I need the whole gamut of possibilities, or are they really just focusing on one component of what's going on? Okay, so let's take a look at a few more details, and then we're going to do an actual example in your notes. Multiplication rule for tree diagrams. For a multi-stage experiment, right, kind of like the drawings I was just going with, the outcome along any path of the tree diagram is equal to the product of the probabilities along the path. For example, if I finish drawing this as red and not red, I'm abbreviating now, red, not red, and I wanted to know what's the probability of drawing two reds, I would multiply these two branches together. They would each have a probability along their branch. The probabilities might be the same or they might be different, but we're just going to multiply what each of the branches' probabilities are, and that would be the probability of that whole branch working out in the end. There's a note here. There are other ways of doing these problems, okay? But I do expect to see a tree diagram or something equivalent, and I'll show you what I mean by something equivalent as well, on all your problems, not just a series of multiplications and additions. And the primary reason for that is because if you were teaching this at a younger grades, that's the kind of thing you'd be teaching, right? You wouldn't be teaching all the numerical pieces of it. You'd be teaching the structure of it and how to think about it. And so I got to make sure that you understand the structure and how to think about it. So make sure you allow space. So sometimes I know we skip some space because we don't know how to do a problem. You might want to skip more than space than normal as you're having that happen, because it's going to take some space to draw these out. All right, independent events. Independent events are events in which the occurrence of one event has no influence on the outcome of a second. Like games are a really good example of this, where we replace things. So like the card example that we were talking about before, if we pulled the card out of the deck and we put it back in, then we are just as equally likely to pull that card again as we are to pull any other card. The first draw has no effect on the second draw. Some other independent events, like if you think about rolling dice, your first roll of the dice has absolutely no bearing on what the second roll of the dice is, right? Flipping coins, right? First flip has nothing to do with the second flip. Another one that's really kind of funny, and we'll have an example of it later too, is the gender of babies being born. Just because you've had 5 boys already does not mean that baby number 6 is a girl. It doesn't work that way, right? Every single child has an independent probability. They're independent events. If your events are independent, then the following equation holds. Now, we saw this notation just a moment ago. Some of you, for maybe the first time if you hadn't had number theory. This is telling us it's the intersection of two events, so both events happening. So if event 1 and event 2 are independent, no effect on one another, right? You rolled the dice and you flipped the coin. Or you even just flipped the coin twice, right? Independent events from flip 1 to flip 2. Then the event that both things are going to happen is simply the multiplication of the individual probabilities. The probability of the event of both things happening. So what's the probability of the event of having 2 boys? Well, it's the probability of having 1 boy times the probability of having boy number 2, right? You multiply them together. And that's actually what's happening along our tree branches. When we set up our tree branches, we set the tree branches up themselves, by the way we set up our probabilities, to have independent structure to them so that we have the ability to multiply along those tree branches. Okay, so we should definitely do the example for Hawaii, right? Absolutely. An executive committee consists of 10 members, 4 women, 6 men. 3 members were selected at random to attend a meeting in Hawaii. Okay, got the system so far? There's 10 people. We're selecting 3 at random. Imagine just dumping their names in a hat. Now, in theory, they're all independent people, obviously, and we could do a branch for every single person. But that's not really necessary here. And the reason it's not necessary is because the only distinguishing feature that this problem asks about is whether they're male or female. So in very much the same way of this red, not red, it's like that. I don't care about the fact that there are individual people. I'm only categorizing upon male versus female. Probably because I got to figure out how many rooms I got to reserve. I mean, seriously, right? Like there's reasons for these kinds of things to happen. So when we're looking at this particular problem, we're reaching in a basket and we're pulling out a name. And the name corresponds to a person and they're male or female. So our first draw out of the hat will result in a name, and the name will either be a man or a woman. You can do male, female if you wish. I'm going to do MW for male, female, or for man, woman. The first time we draw out of the hat, how many men's names are in the hat? 6 out of 10. How many women's names? 4 out of 10. So a complete tree diagram will have those pieces on there. But that's just choosing the first person to go to Hawaii. We have to then leave that name out because the person's not going to Hawaii twice, right? It doesn't make sense to put the person's name back in. Are you with me? So there's no longer 10 names in the hat. There are 9. Okay, everybody good so far? 9, yeah, just like that. Okay. So we reach in again, no matter whose name we've drawn, we are reaching in a second time. And the second reach, again, will yield either a man or a woman. Well, their name anyway. But there are not 10 people in the basket anymore. There's 9. So all these fractions will have a denominator of 9, which is actually the reason that I didn't want to put this in decimal form, because I knew that 9 was coming up. Those are my fractions denominators. Okay, so let's go along the first branch. Along the very first top branch, I've already selected one male, right? So if I'm along that branch, how many men's names are still in the basket? 5, because one of them was already selected. So if there's 5 men, how many women are there? There's still the same 4, right? Now we're going to do the bottom branch. Along the bottom branch, I selected a woman's name, the first draw. So how many men are still in the basket in that situation? 6. And how many women?
3.
There are 3. So sometimes the probabilities will change along our branches because of the context of the problem. And this is an example of one. Okay, but that's only 2 people going to Hawaii, and we're supposed to have 3, so we're going to do one more set of branches. And you can see why we need so much space, right? The more events that we do, trials of our experiment we do, the bigger the tree becomes. I think the biggest any of your trees become is 4 events, just so you know, in your homework. Yeah, I think it's flipping a coin or something like that too. Okay, it's still all man, woman, right? Man, woman, man, woman, man. It's not 8 people. You're only selecting 3. So only one of these branches is going to be reality. So maybe it's like that one. That's 3 people. The first one was a woman, second was a man, third was a woman. That's why you've selected 3, is that at each branch spot, you're selecting one person. We're just writing down the options of who could have been selected.
So is like the denominator 8 now?
Yes, the denominator will be 8. I'm sorry, I misunderstood your question. So sorry. Yeah, there are only 8 names in there now. You're right. So there are only 8 names still to be selected from among. Okay, so along the very, very, very top branch, we've selected 2 men. So how many men are left? There are 4. I can't write there, so let's shift this over here. There's 4. You can barely see it. And how many women? So 4, right? Okay, so now we are along this branch where we've selected a man and a woman, one of each. How many men's names are left? 5. And how many women? 3. Now, interestingly enough, this branch where I selected a woman and then a man is actually the exact same probabilities, right, as the one before. The order didn't make any difference. I still have 1 fewer man and 1 fewer woman than I had before. So those actually still will be the ones I had above. So this is 5 out of 8 and 3 out of 8. then my last branch where I selected 2 women, how many men are left? 6, and men? I'm sorry, women?
2.
2, yeah.
I'm ready for that last one.
The 3 women to go together, have fun in Hawaii. Okay, your next page actually asks you the questions that you're going to use this tree diagram to answer. So this first question is actually the one Abby just said she was rooting for. What is the probability that all 3 selected are women? Okay, so we had a feature over here that talked about multiplication for tree diagrams. And it said that in order to find the outcome along a single branch, we can just multiply the individual probabilities along that branch. So our branch that we are being asked about on part A is this branch, right? So those are the 3 probabilities that I'm going to be multiplying. 4 tenths, 3 ninths, and 2 eighths. So I'm multiplying 4 over 10 times 3 over 9 times 2 over 8. Now we've already done a fair bit with fractions back in chapter 6, okay? You can multiply across the top, multiply across the bottom, and then reduce if you wish. But you can also reduce between numerators and denominators and across diagonals as you go. And that's probably our simpler route to go, right? Like 4 and 10 both divide by 2. So this is really just 2 over 5. 3 and 9 both divide by 3. So this is really just 1 over 3. And 2 and 8 both divide by 2, giving me 1 over 4. Now, you might also look along diagonals. If you wish, you could. Certainly the 2 in the top left and the 4 in the bottom right could be reduced. But let's just say you didn't notice that. You reduced them all individually, and then you multiplied. You're going to get a 2 on top, and then we're going to get a 60 on bottom. So at the end, you do the reducing as the last step, too. It doesn't make any difference, but your final answer should be in reduced form, 1/30. It's not very likely, right? Not real likely. For several reasons. Number one, it was one single branch that resulted in that outcome, right? I didn't have lots of branches. Like if I just want any 2 women, there's lots of branches that had 2 women along them. We'd have to look at all of them. The other thing is that there was fewer women than men to start with. So that's another reason why that number's so small. Next question. It says, what is the probability that at least 1 man is selected? So I want you to look back at your branches and tell me which branches have at least 1 man on them.
All of them except the women one.
And that's actually a really good way to think about it. Instead of considering all the ones that have a man along the branch, let's consider the one that doesn't. There's only one that does not have a man on the branch, right? The very bottom one that we already looked at. So we had a theorem last time. What we want here is that we want the probability of at least 1 man. That's what we're being asked. But it's actually easier to find what's called the complement of that, which is 1 minus the probability of it being all women. Right? What do I not want? Well, I don't want it to be all women, so it's 100% or a 1 probability minus the likelihood that it's going to be all women. And we already did that part. I already found this. It's 1 over 30. So what is 1 minus 1 over 30? 29 over 30. It's extremely likely that at least one of our gentlemen are going to be headed to that trip. I mean, that's high. If you want to put in your calculator, you're going to be something somewhere around 97%, I think, something like that. It's pretty likely, Okay, so this is how we would draw a tree diagram and how we would use it to do things. But we could be asked other questions, right? We could be asked, well, what's the probability that 2 men get to go? So let me just talk about that real quick because I don't have an example that addresses that directly, and there are some of your homework questions that do. If that happened, where it's not all or nothing, because that's kind of my questions, they ended up being all or nothing, right? I'd have to go through each branch that had, we'll say exactly 2 men, just for the sake of argument. This is 2 men and a woman, so that's 2 men. This one would be 2 men and a woman. And this one right here would be 2 men and 1 woman. Okay, all three of those ending those are three separate branches because they all end at a different location. So there are three different paths that got me there. If I wanted to find the probability of that happening, I'd multiply along each branch, just like I did for the all women one here, okay? But then I'd have to add the numbers together, right? Because there's one probability of choosing man, man, woman. But there's another probability of choosing man, woman, man. And there's a third probability of choosing woman, man, man. And then we would add the three together instead of, there's no multiplication when we combine them at the end. It's multiplication along the branch, adding in the branches at the end. Okay, so the next couple of examples actually show what I mentioned over here where I said something equivalent, which is super vague. So I'm going to show you what I mean by something equivalent. You can use tree diagrams on these as well, but sometimes there's kind of a nicer imagery of how to think about a particular problem. So we're going to look at that on this example. We have a box, and the box contains 5 slips of paper. Oh, I'm sorry, we're out of time, aren't we? I'm so sorry. I'm so excited. We'll pick up on our box with our example next time. So sorry.